Welcome to the Corrosion Corrosion channel. My name is احتشام زاده. An introduction to this channel is available on video number E28. Chapter 3, Section 6, Types of Corrosion. Sulfidation, affected units or equipment, appearance or morphology of damage, prevention, mitigation, inspection and monitoring. The main reference is Damage Mechanisms Affecting Fixed Equipment in the Refining Industry, API RP 571. Description of damage. Sulfidation is corrosion of carbon steel and other alloys resulting from the reaction with sulfur compounds in high-temperature environments. Corrosion in the presence of hydrogen, high-temperature H2H2S corrosion is discussed in video number E53 on this channel. Also, in video number E54, the first section of sulfidation is available, including 1. Description of sulfidation, 2. Affected materials, and 3. Critical factors. Now, 4. Affected units or equipment. A. Sulfidation occurs in piping and equipment in high-temperature environments where sulfur-containing liquid, vapor, or mixed streams are processed. B. Crude, vacuum, FCC, coker, and visbreaker units, as well as the feed sections of hydroprocessing units upstream of hydrogen injection, at which point high-temperature H2H2S corrosion begins to govern, commonly process these high-temperature sulfur-containing streams without or prior to intentionally added hydrogen. C. Coker heaters fabricated from high nickel alloys such as alloy 800H have shown accelerated sulfidation corrosion rates in the lower radiant sections operating with tube metal temperatures exceeding 1193 degrees Fahrenheit as compared to similar tubes operating below this temperature. D. Heaters fired with oil, gas, coke, and most other sources of fuel may be affected depending on sulfur levels in the fuel. It is not uncommon for heaters to be fired with anything but gas, usually low sulfur gas, to meet environmental restrictions, especially in the United States. 5. Appearance or morphology of damage. A. Depending on service conditions, corrosion is most often in the form of uniform thinning, but can also occur as localized corrosion or high-velocity erosion-corrosion damage. Figures 1 to 5. Figure 1. Sulfidation failure of an 8-inch carbon steel pipe. Note the relatively uniform thinning that resulted in a sizable rupture. Figure 2. Sulfidation failure illustrating the effect of accelerated corrosion due to low silicon content. This 8-inch pipe section in FCC bottoms piping was in service at 150 psig or 1 megapascal at 650 degrees Fahrenheit to 700 degrees Fahrenheit. The piping sketch in the next figure illustrates the difference in corrosion rates as compared to adjacent high silicon components. Figure 3. Thickness survey of 8-inch pipe shown in the previous figure. Overhead pipe, elbow, pipe above the pop piece measured from OD, remainder of the failed pop piece, top of T, T, bottom near T, bypass flow, and primary flow. Figure 4. Sulfidation failure of a carbon steel side glass nipple on the right after 2 years in a crude unit. Original thickness is shown on left for comparison. Material was supposed to be 9% chromium, 1% molybdenum. Figure 5. Sulfidation failure of piping elbow. 6. Prevention mitigation. 1. Resistance to sulfidation is generally achieved by upgrading to a higher chromium steel such as 9 chromium 1 molybdenum. 2. Piping and equipment constructed from solid or clad or overlaid 300 series stainless steel should provide significant resistance to corrosion. 400 series stainless steel cladding should also provide significant improvement over carbon steel. Solid 400 series stainless steel is generally not selected for piping or other pressure containing equipment because of embrittlement and fracture toughness concerns. 3. Aluminum diffusion treatment of carbon steel and low alloy steel components is sometimes used to reduce sulfidation rates and minimize scale formation. However, it may not offer complete protection. 4. For operation above 1193 degrees Fahrenheit, sulfidation rates of higher nickel alloys can be reduced by selecting an alloy with a lower nickel content. 7. Inspection and monitoring. 1. Thinning in piping, tubing, and other equipment can be detected and measured using ultrasonic testing, thickness measurement, or radiography testing. Thinning in pressure vessels and large diameter piping where internal inspection is possible can be detected by internal visual testing, typically followed up with ultrasonic testing. 2. Permanently mounted thickness monitoring sensors can be used. 3. Thinning in heater tubes can be detected using ultrasonic testing or by smart pigging. Smart pigging provides significantly more coverage than spot ultrasonic testing and may find thinning missed by spot ultrasonic testing. 4. Actual operating temperatures should be verified and compared against design. Temperatures and sulfur levels should be monitored for increases above design. 5. Temperatures can be monitored using tube skin thermocouples and/or infrared thermography. 6. Proactive and retroactive MVPs materials verification programs can be used for alloy verification and to check for alloy mix-ups in services where sulfidation is anticipated. API 578 provides guidance on MVPs. See Figure 4, slide number 1025. 7. Most refiners have instituted programs to identify low silicon carbon steel piping or components in sulfidation service by measuring the thickness of component in vulnerable piping systems. A small number of refiners have followed a PMI type approach to measuring or otherwise determining the silicon content of piping components. Challenge number 55. Thank you for your time and attention. If you like to challenge yourself, please answer these questions in the comments section. 1. In which condition does sulfidation occur in piping and equipment? 2. How is resistance to sulfidation generally achieved? 3. What are the advantages of smart pigging in comparison with other inspection and monitoring methods?